Well, here we have part D on this acid-base problem. We've got ourselves our weak base and amine, that NH2 is the equivalent of ammonia, except it's an organic attachment to it. We're adding a strong acid to it, and this acid, proton, will bam, right on there, and neutralize this amine, making this weak acid a benzamonium. They say, calculate the pH at the equivalence point of the titration in this reaction. Well, this is a titration where we have our acid and our base, making, finally in this case, the conjugate base, and we're set. It's just a simple titration equation where normally we would just take the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. They want to know the volume of 0.3 molar, this is our strong acid, needed to titrate 40 mLs of 0.3 molar aniline. Wait a second, that's pretty darn easy because the concentration of both of these is the same, so pretty obviously you're going to need the same amount of acid, the same number of moles of acid, 1 to 1. So, I mean, you could end up using this equation to solve it, but there's no real need to do that. All we've got to do is realize that if you had 40 mLs of base, you're going to need 40 mLs of acid, 40 to the nearest tenth of an ml, using a burette accurately probably, of the acid. So that's no big deal. They want to know the millimoles of the base we made. Okay, that's the amount of base that's produced in this titration. Well, that's going to be easy. It's going to be the volume of the base times that concentration. So I'll just pull up my calculator. So all I've got to do is say, okay, we had 0.3 molar and we had 40 mLs of it. I'll just type in the 40 and get our answer. And we have 12 millimoles, 12 thousandths of a mole. 12.0. That's much nicer than having to write 12 times 10 to the negative 3 or 1.2 times 10 to the negative 2. The next thing that they want is the volume of solution at the equivalence point. Well, let's see. We had 40 mLs of base and we added 40 mLs of acid to it. So we're going to presume that the volumes are additive, and we're going to have a total of 80 mLs, which is the total volume of solution at the equivalence point. What we're leading to in this question is what's the concentration of this weak base? Because we now have a weak base that's been produced. This is the stuff that's in solution now. The weak acid that's in solution. Now here we had our weak base and the strong acid reacted with it, and our product is going to be the conjugate acid of this weak base. Earlier in this problem, you had to find the Kb of the base. And once you have the Kb of a base, you can figure out the Ka of its acid just by dividing by 1 times 10 to the negative 3. And that was asked earlier, and already we know the Ka of this acid. Well, let's do the calculation anyway, even though you did it earlier. 1 times 10 to the negative 14 divided by the Kb will give us the Ka. We've done that quite a few other times, and the Kb was 4.4 times 10 to the negative 10, a real weak base. And now we have the Ka of the acid, and I'll type that in now. 2.27 times 10 to the negative 5. Rounded off. Ka doesn't have a unit. This is an extremely weak base and makes a slightly stronger conjugate acid. So we now know our Ka. They say, what is the pH at the equivalence point? Well, we know it's going to be slightly acidic because we've got a weak acid in here. What's the equation? How do we find out about things? Oh, wait a second. We need to know the concentration of our weak acid. But now we've got 80 mLs, so that's going to be pretty easy. We can just say, hey, that's going to be half that because basically we've diluted it. And so we can just say 0.015 molar acid, or you could have done it calculating, say I've got 12 millimoles. In fact, let me get back to my calculator again. 12 millimoles divided by 80 milliliters, and that'll give us molar concentration. Hey, indeed, 0.15 molar, exactly what you expect. But okay, we've got the concentration of our weak acid now in solution. We've got its Ka. How do we find the hydrogen ion concentration? Well, that was back on the very first outline. Let me pull that outline out. Here it is. Here it is. The bottom line, when you have any weak acid, and we have a real weak acid here, we can find out the hydrogen ion concentration approximately, close enough, without having used a quadratic, by the concentration of the acid times its Ka. So let's go and take care of that to solve this question. To figure this out, I'm going to get my calculator out again. We need the Ka times the concentration. Well, we already have the concentration of 0.15 molar, and we're going to multiply that times the Ka of the acid, which we have, 2.27 times E, 10 to the negative 5, and we've got the multiplication of the concentration times the Ka. Now we just have to take the square root of that, second function, square root in this case, and rather than typing this out, I'm going to go, and I'll let you take care of that, because that'll be the concentration of the acid. Okay, we've got that taken care of. Another acid-base problem, in this case a titration that produced a weak acid solution, and we found out the concentration of the weak acid, and it's Ka, and it was just a piece of cake to find out the H+. And of course, you can figure out the pH once you've got the H+ concentration.